So this section is on the Earth, the Moon, and the sky. I talked a little bit about how we measure locations in the previous video, but just to be clear, we measure positions on Earth with two angles called the latitude and the longitude. It turns out the latitude is how many degrees you are up from the equator or down. So you can have north latitude, usually called positive numbers, or you can have south latitude or negative numbers. Weatherford is about 35 degrees north latitude. This is actually Washington, D.C. here. Weatherford's off over here, if you can see my little cursor there. And then the longitude is the angle around the Earth instead of up and down, north and south. It's the east-west one. The 0 for that is in Greenwich, England. And you measure degrees. We're degrees west or negative, so we're 98 degrees west latitude, west longitude, and 35 degrees, about 35.5 degrees north latitude. It's a similar thing on the celestial sphere. We set up a circle and we just mark the positions of stars on the celestial sphere. So this is just a picture in Greenwich, England of the 0 line. Everybody sort of agreed that it's going to be at this spot at the Royal Observatory in Greenwich, England, one of the first observatories built, at least in Western culture. Recent Western culture, how about that? Because there have been observatories that go. Stonehenge is kind of an observatory, and that was built almost 5,000 years ago. This is you'll see these occasionally in museums. University of Oklahoma has one here in Oklahoma. This is called a Foucault pendulum. And what's kind of interesting about it is that as it swings, the Earth kind of turns underneath it. And so this is the pendulum bob here, and you can kind of see a cable going up. It'll swing back and forth and knock over these pegs that you see going around the edges. And over the course of a day, it should knock down all the pegs. It depends actually on what latitude you're at for that to happen. But it was pretty good evidence in the 1800s that the Earth is turning, among others. But it's a common exhibit in museums. So this is a picture of the Earth going around the sun. I'm going to show you a lot of these today. A couple of important things to remember. One is the Earth's and sun size are not to scale, and the distances are generally not to scale. And so this is just illustrative. But we've already seen these little white lines are the polar axis of the Earth. The upper one is the north and the lower one is the south based on the maps. You can kind of tell. And notice the Earth is like a spinning top. It always keeps its orientation the same way. It's like a gyroscope, I guess, not a spinning top because they tend to wobble. So as the Earth goes around, sometimes its north pole is tilted away from the sun, and sometimes it's tilted toward the sun. So here at the summer solstice on June 21, you can see the northern hemisphere is tilted toward the sun. Now, since it rotates about this angled axis, you can see as it rotates for 24 hours here, everybody in the light spot, everybody at the North Pole or near the North Pole will get 24 hours of sunlight because that axis is just tilted in, and even though the Earth turns, it's turning about this axis, and you'll see and Santa Claus will get 24 hours of sunlight. Santa Claus at the North Pole will actually get 24 hours of sunlight for quite a few days as it comes around this bend. But there are also people who are farther away from the North Pole who will still get 24 hours of sunlight on the solstice. In fact, if you're standing at the vertical point right here, at least at the summer solstice, you'll get 24 hours of sunlight. That angle away from the North Pole, that 23.5 degrees, marks the Arctic Circle. If you're within the Arctic Circle, you'll at least get 1 day a year with 24 hours of sunlight. And when you're tilted the other way, you'll get at least 1 day a year of 24 hours of darkness. If you live in the Arctic Circle, notice Santa Claus gets 24 hours of darkness on December 21, on the 25th also. So what's winter in the northern hemisphere is summer in the southern hemisphere, because now the South Pole is tilted toward the sun. And what's summer in the northern hemisphere is winter in the southern hemisphere. The seasons are really about how tilted you are towards the sun. Notice if the Earth didn't have any tilt in its axis, we wouldn't have any seasons. Everybody would get the same sunlight. Their amount of sunlight wouldn't change through the year. It's the fact that the axis, the polar axis, the rotational axis is tilted that causes the Earth to have seasons. As a consequence of those seasons, sometimes the sun is higher in the sky and sometimes it's lower. When it's higher in the sky, the sun is more intense. It's more packed. When the sun is lower in the sky, the rays are spread out. This is just a meter wide beam, right? When it hits the ground from almost vertical, it's 73 degrees up, you get something that's pretty close to a meter wide, but when it hits the ground at a lower angle, that same amount of sunlight is spread over a wider area, and so it's less heating per area. So the right is a winter scene, and the left is a summer scene. This is another way to illustrate the same point. Here we have the celestial sphere and somebody just standing on a spot on the Earth, but we just draw it as a giant plane, right? And so you're standing there, and over the course of the day, the sun goes around, right? It rises and sets. Well, if the sun is, if it's in the summer solstice, you see it, the sun is high in the northern sky. So let me just go back a page for a second. No, 2 pages, right? If you're over here, the sun looks high in the north, right? Whereas if you're over here, the sun is high in the southern hemisphere. I don't know if you can see that very well. We'll come across another picture of that here in a minute. On the equinoxes, the sun just sort of splits the sky. It travels right around the center. And so then in the winter, so somebody's looking at the sun in the winter, the sun rises and sets south of the east-west line, and it's low in the sky, like this picture here. You see the sun low in the sky. In the summertime, the sun rises north of due east and sets north of due west, and it's high in the sky. You get more daylight in the summertime, and the sun is higher in the sky, so it's brighter. You get less daylight in the wintertime, and the sun is lower in the sky, so it's dimmer. So those are the 2 reasons why summer days are hotter than winter days. Longer days and more direct sunlight. So now if you look at it from a slightly a different point of view, if the sun is way off to the left there, then when the axis is tilted towards when the polar axis is tilted towards the sun, we get more direct sunlight here in the northern hemisphere. In fact, at the solstice, you can see that the sun is kind of directly coming down on the spot right here. Let me see if I can draw this a little bit. I'm just going to. So that same picture, I'm just going to draw it this way, right? And here's the equator. I know these aren't very good pictures. Here's the equator. Here's the equinox. I mean, here's the tropical Cancer. Let me try it one more time. It's like this. Let me see if I get a better circle. I think I got a better circle that time. So here's the polar axis. Here's the equator. It's like this. Sorry, there's the polar axis. So this is the North Pole. This is the South Pole. This is sunlight coming in from this way, right, like this. If you notice, it's coming down almost perpendicular on this spot right here. This guy's tilted away a little bit. Up higher is tilted away a little bit, but this guy's coming in almost straight. And like we were saying in the last slide, this is the Tropic of Cancer. This is the northernmost point on the Earth where you get the sunlight directly overhead. If you were standing up here somewhere like this, the sun is never going to be overhead. The sun is never going to be this way. This is the farthest north. The sun will appear directly overhead. This is the farthest south. So let's look at these. Let's go back to this one, right? So the farthest north the sun appears is the Tropic of Cancer. The sun gets directly overhead is the Tropic of Cancer, and it does that on the summer solstice. Now let's look at the winter solstice. Right? On the winter solstice, now the Earth's northern axis is tilted away. Notice where the Tropic of Cancer is, the one that was just lined up with the sun. Now when they're looking at the sun, they're looking low above the low in the sky in the southern direction, right? They'll be looking off this way at the sun, and that angle is tilted from vertical. Right now, the people who are looking straight up to see the sun are at the Tropic of Capricorn. So on the summer solstice, the rotational axis of the Earth has its greatest tilt in the direction of the sun. On the winter solstice, the rotational axis of the Earth has its greatest tilt away from the direction of the sun, right? At least for the North Pole. The Tropic of Cancer is the most northern latitude that gets at least one day where the sun passes directly overhead. The Tropic of Cancer is the most southern latitude where that occurs. The Arctic Circle is the farthest point from the North Pole that gets at least one day per year with 24 hours of sunlight. Let me just page back up again. Again, when I'm saying the polar axis, I'm saying when the North Pole is tilted away, that's the winter solstice. When the North Pole is tilted toward the sun, that's the summer solstice in the northern hemisphere. Okay. So let me talk. We're going to talk a little bit about time here, and there's some tricky things about time that are complicated, and I'm just going to start by saying, let's look at this person on the right here. I'm going to draw this on my board here. So this is a person standing on the Earth, and never mind the scales again, right? And if I asked you what time of day this was, hopefully you would say this is noon because the person's directly overhead. And then I might ask you, well, how much time till the next moon? Noon. And you say, well, 24 hours. It's going to spin back around and get back to this spot, and it'll be noon again. Here's the tricky part of that. Is that the Earth, in addition to rotating on its axis, is moving in its orbit around the sun. And so if it were to do one complete rotation, you can kind of see it there, can't you? If the Earth were going to do one complete rotation, then the little man would be aligned along this solid white line, right? Because the little man would be horizontal. In fact, in order to get back to noon the next day, it has to do a little more than one complete rotation. Just let me draw it over here. Right? So I'll draw it the way they drew it. So here's my path, right? And here's the guy standing on the Earth, right, like this. And here's the sun over here, right? And let me draw the sun over here. So there's the sun, right? It's directly overhead. And now the Earth moves over to here. And if I were going to say one complete rotation, the guy would be standing this way, right? Because the Earth has gone around one complete circle, right, in both of these cases. The catch is, it's not noon for this guy. In order for this guy to get to noon, he's got to be pointed towards the sun again, which means he has to turn a little more than 360 degrees. And so we define, let me go back to this picture now. We define a solar day as for the time to return to the exact same position in the sky. In other words, sun straight overhead to sun straight overhead. That's what we call a solar day. A sidereal day is the time for the Earth to rotate once on its axis. So in this case, it's solid white line to solid white line. That's the sidereal day. People are more interested usually in a solar day. How much time is between noon today and noon tomorrow? And there's only a few minutes difference between those two, but they're not quite the same thing. Because the Earth is round, the sun rises later as you move west, right? If it's sunset right now, then the sun won't rise west of here, like in New Mexico, maybe for another hour or something like that. Actually, more like California. But anyway, you get the idea, right? So when the sun has passed halfway through its daily path across the sky, it has not gotten to that far in a city further west, right? So we give Western cities earlier times. The time it takes the sun to cross the U.S. is about 3 hours, and so we have time zones. It turns out you can do the math on that and say, well, look, the Earth turns 360 degrees in 24 hours, and that's about 15 degrees per hour. And so what we usually do is about every 15 degrees on the planet, we move the time back an hour. And so that, Chicago is an hour behind New York, and Denver is an hour behind Chicago, and Los Angeles is an hour behind Denver, and so on. And so as we go around, we drop an hour every 15 degrees west you go. Well, after you complete another circle all the way around the Earth, you would be a day behind because you would keep backing up an hour. But now you're back where you started from. And so what we do is we create an international date line, where the date changes. And so if you start at the international date line and move west, it gets an hour earlier every 15 degrees, all the way to get back to the international date line, where now it jumps back to the next day. So if this was like right now, if you move all the way around the Earth, this would be almost a day ago. And so the guys to the west of this line, the left of the right line, are a day ahead of the guys just to the right of it. That's why it's called the international date line. And this gives people approximately noon when it's overhead in your area, when the sun is overhead in your area. People have been timekeeping for millennia, and following the seasons and doing all kinds of stuff like this. This is just a picture of Stonehenge in England, which you should visit if you ever get a chance. It's an ancient arrangement of rocks that kept track of the motions of the sun and the moon. People are still speculating on exactly how it was built. This is Mayan temple observatory in Chichen Itza in the Yucatan in Mexico. It dates from around 1000 current era, AD, I guess. The Mayans made holes in their roofs that will allow the sun to shine through on certain days. So let's talk a little bit about the motion of the moon. So the moon is an important object from the Earth and has been for our civilizations for a long time. If you really want to understand what the moon does, the moon has phases. We know about a full moon. Maybe you've seen a first quarter, a new moon, or something like that, right? And so here's a picture of what actually happens. Once again, these drawings are not to scale. Actually, the moon is about 30 Earth diameters away. The moon's diameter is about a quarter of the Earth's, which this isn't a terrible version of that. It's not quite. This one should be about half. The moon should be about half as big, probably, as it is. But it should be 30 Earth diameters away. That's how far apart they should be if this is a scale drawing. So notice, as we look at this picture, that sunlight is shining from the sun, which is very, very far away to the right, way off scale on this. The sun is about 10,000 Earth diameters to the right, or something like that. So, so what I want you to notice, never mind the moons that are around the outside, the moons that are orbiting the Earth are on the blue ring. Notice that they're all just lit on the half that's facing the sun. The Earth doesn't have much to do with it. In fact, the Earth also is lit on the half that's facing the sun. The sun is what lights everything up. Otherwise, we would be all dark. The moon and the Earth don't give off any light of their own. And so, in every one of these, the moon looks exactly identical from where we're sitting now. But if you were standing on Earth, it would be different. So if you look at yourself, imagine yourself on the left half of the Earth, right at the edge here, you'd be at midnight, right? It would be in the most dark region of the Earth, right? And if you're looking at Moon E, you would actually see a full moon. That's what this picture says. It says, look, From anywhere on Earth, this moon would be perceived as full. Remember, the scale is crazy wrong here. And so the Earth would actually be 30 diameters away, and the Earth would be pretty small compared to the distance between these two. And so the moon looks roughly the same from anywhere you are on the Earth at a given time, assuming you can see it. And so you would see a full moon here. You'd see the full lit side. On the other hand, if you looked at this moon on the right, the one that's kind of between you and the sun, you would see just the dark side of the moon because the lit side is facing the sun. And so you would see what we call a new moon. And so if you see the whole moon lit up, you see a full moon. If you see just the dark half of the moon, you see a new moon. Well, as the moon goes around, you see more and more of the lit side. So the moon orbits in this direction, and counterclockwise as this drawing is done. And so it moves to waxing crescent. That's what we call the waxing means increasing. So the crescent is increasing. First it was dark, then we got a crescent. This is first quarter because it's a quarter of a way around the circle, right? First quarter, you see half the moon is dark and half the moon is light from what you can see. We know at any given time half of the moon is lit because it's just the half facing the sun. Similarly, if the moon's at position D, now you see a mostly lit moon. We call that a waxing gibbous. Gibbous is a word for, it means, large or fat. Then you see a full moon. And now, once again, just like at position D, at position F, you see mostly lit. We call that waning gibbous. Waning means getting smaller. Then we see third quarter, and then we see waning crescent, and then we're back to new. And so these outer pictures tell you what the moon looks like in positions A, B, C, D, E, F, G, and H. If you're looking at those A, B, C, D, E, F, G, and H positions as viewed from the Earth. Okay, how the moon rotates. This is another interesting thing about the moon. You'll often hear that the moon doesn't rotate because if you look at the moon on any given night, you're always looking at the same side of the moon. The moon always keeps one face towards the Earth. Well, if the moon wasn't rotating, you would get the top picture, where it would always be facing one direction in space. But in fact, the same part of the moon is always facing the Earth, so the moon is rotating at exactly the same rate it's going around. And so it does one rotation on its axis. It has like one day for every orbit it does of the Earth. So it rotates pretty close to once a month. All right, let's talk a little gravity. So this is tidal forces on the Earth dive to the moon. It should say due to the moon. Let me see if I can fix that real fast. That's better. So I'm going to do a hand drawing of this just for maybe your entertainment. So let's say this is the moon, right? Let's say instead of having the Earth out here, I had 3 balls out here, right? I think we could agree that because of the force of gravity, remember the force of gravity is G times the mass of the moon, in this case, times the mass of one of these objects. We'll say they each have a mass m. They're 3 identical billiard balls, divided by the distance squared, where the distance is the distance between them, right? Between the moon and the object. So because they all have the same m and the mass of the moon doesn't change, the numerator in these guys is the same. But in each case, the d gets a little larger as I move farther away. And that means the force of gravity on this guy is stronger than the force of gravity on this guy, which is stronger than the force of gravity on this guy. And so the moon pulls with a bigger force on this one, and a medium force on this one, and a weaker force on that one. The effect of that is to pull these things apart. It's called a tidal force. And so since it's pulling less on this one and more on this one and even more on this one, it tends to want to tear the thing apart. That's what tidal forces do. And so that's what's happening to the Earth by the moon. By the way, the Earth did this to the moon even worse, and that's why the moon always has one face towards us. The Earth stretched the moon out and then locked onto that near edge and brought the moon to a stop. And so the moon's kind of doing it back to us, just a lot more slowly because it's tiny and we're big. So what effect does that have? It turns out those differential forces cause the oceans, it has most effect on bodies of water like the oceans. And so if you have an ideal ocean, just an ocean over the whole surface of the planet, then if the moon is to the right, then the front edge will be bulged because the water is most easily moved and the force is strongest here. And then there'll also be a bulge behind because this guy has the weakest forces and he gets left behind. And so you see two places where you get extra water, and then perpendicular to that, two regions where you get less water. And so what you have if this is my planet, right, and here's the moon, you get a bulge over here and a bulge over here, and you get a high tide here and here and a low tide here and here. And so if the moon is overhead, or if the moon is underfoot, right, if you're standing this way and the moon is through the earth from you, you get a high tide. If the moon is on the horizon, again, not to scale, if the moon is on the horizon, you get a low tide. This is complicated a little bit by the sun, because the sun actually makes a smaller tidal force on the earth than the moon does. The reason isn't because the sun's gravity is weaker, it's because the sun is so much farther away. And so when the sun and the moon and the earth make a line, you get extra big tides that are called spring tides. In spring tides, the sun and moon's poles reinforce each other. They just need to be in a line, right? If the sun and the moon are perpendicular relative to the earth, then they kind of cancel each other out. So let me just draw these for a second. So if this is the earth, right, and this is the moon, and up here is the sun, right? I'm not doing a very good job. The sun is trying to stretch the earth this way, but the moon is trying to stretch the earth this way, and they kind of cancel each other out a little bit. The moon's a little stronger, so you still get a little bit of tide due to the moon, but it's not as big. Whereas, if the sun, the moon, and the earth make a line, and that could mean any kind of line, so I could have the sun over on this side, or I could have the sun over on this side, or to put a more fine point on it, I could say, here's the moon, or here's the moon. In either one of these positions, for the moon, the sun is off to the right, you would get an earth that's extra stretched, because both the sun and the moon are trying to stretch it this way. Again, they just pull harder on the closer side and weaker on the farther side. And you might think that it would be different if the moon was on the other side, but it doesn't matter which side the moon is on or the sun. If they're in a line, they're all pulling the same, stretching the earth the same way. And so we get these tides. Newton, once he came up with his law of gravity, explained tides, and that was a big deal because those things affected people's lives, and they understood why they happened after that. And so it was Newton did a lot of things to make himself a rock star, but that was one of them. He was much more famous in his time than scientists are now, I think. Okay. Let's talk a little bit about eclipses. So let me get back to my screen. There we go. And so here's the sun, and here's an object. This blue object here can either be the moon or the earth or any other object. When the sun shines on something, that object casts a shadow. If you're in the umbra, you're in a region where none of the sunlight can be seen. So in the umbra, none of the light source can be seen. So if you look at A, the shadow cast by the spherical body of the moon, for example, is shown. Notice the dark umbra and the lighter penumbra. 4 points in the shadow are labeled with numbers. In B, you see what the sun and moon would look like under those points. So at position 1, here at position 1, you would see a total eclipse, right? Because you wouldn't see any of the sun from that spot. At positions 2 and 3, you would see a partial eclipse. You would see part of the sun in these regions. There, and you're in the penumbra. And then in region 4, you would see what's called an annular eclipse. So you should be able to match up these numbered boxes below with what you would see from the corresponding position in the top figure. So the left would be a total eclipse. If this was the most you saw, you would see a partial eclipse, And this last one is called an annular eclipse, where you're far enough away that you can see a little bit of the light source around the blocking object. So now let's talk about a solar eclipse. A solar eclipse is when the moon passes between the Earth and the sun. In fact, you might think that happens once a month, but it turns out it doesn't, because even though the moon goes between the Earth and the sun every month in its orbit, it doesn't go directly between them. It only gets close to that about twice a year for reasons I won't go into. But the size scale is much bigger than it appears here. And so it's easy for the Earth, for the moon to be just a little bit out of position to get directly between the Earth and the sun. It could be, if you drew a line connecting the Earth and the sun, the moon would most of the time either be below or above that line. And so it wasn't quite casting a shadow. These planes don't line up very well. It only happens about twice a year that the moon gets in a position where that can even happen. And then you look at the moon's shadow, and the moon is a smaller object than the Earth is considerably. And so it casts a tiny shadow on the Earth, like this. And so if you happen to pass under that shadow while this is going on, you get a total eclipse, because this is the umbra. If you're in the penumbra, which is a good bit bigger, you'll get a partial eclipse. You might remember either a total eclipse or a partial eclipse from 2017, which is the last one we had in the United States. So if you were in a region where you pass through the moon's umbra, you are seeing a total solar eclipse. If you're in a region where you're passing through the moon's penumbra, but never get into the umbra, you are seeing a partial eclipse. If you actually see a ring of the sun around the moon, you're getting an annular eclipse. I didn't put that one in. This is a great picture. Okay. So a lunar eclipse, if the whole moon gets into the Earth's umbra, it's called a total lunar eclipse. If part of the moon gets into the Earth's umbra, it's called a partial eclipse. And if the moon only passes through the Earth's penumbra, it's called a penumbral eclipse. So let's just look at those. Ooh, did I lose that one? Okay, I'm missing a picture, so just hang on a second. Okay, so this picture is a little different. Again, the geometry is a little crazy because nothing's to scale here. But you can see that as compared to, let me just go back up here for a second. Notice the moon is a tiny object, and it's a small object, so it casts a tiny shadow on the Earth. The Earth is much bigger than the moon, so it casts a much bigger shadow. And so whereas if you want to see a solar eclipse, a total solar eclipse, you have to be in some tiny little place on the Earth, and in fact the shadow has to pass over the land where people are, and then with the part where you are, and they often don't last for very long and just catch a part of the land. So total solar eclipses, not too many people see them. However, oops, dang it, try again. All right. There we go. There we go, sorry about that. However, the moon is a big object and it casts a much bigger shadow. And so often when we get a lunar eclipse, everybody on the half of the Earth that's facing it gets to see it. And even more than that, of course, because the Earth turns while it's going on. And so a significant fraction of the whole planet of the Earth will see a lunar eclipse, whereas only a tiny fraction, a very tiny fraction, will see a solar eclipse. And so the moon is shown here, sort of passing through. There's some different places the moon can pass through, and so let me just get to those. If the whole moon gets into the Earth's umbra, it's called a total lunar eclipse. If part of the moon makes it into the Earth's umbra over the course of the eclipse, it's called a partial eclipse. If part of it gets into the umbra. And if the moon only passes through the Earth's penumbra, it's called a penumbral eclipse. The next total solar eclipse happens in 2024, and this will probably be one of the best ones for the rest of the century. It'll certainly be the last good one in my lifetime. There was a really good one in 2017, which maybe you saw. We went to see it in Wyoming. You can Google where it is. I strongly encourage you, even if you have no interest in science, to go see it. There's all sorts of interesting things that have happened in history during eclipses. Soldiers laid down their weapons, kings made peace, people were executed because they were viewed as harbingers of doom or greatness or something, good fortune, something. If you experience one of these, if you just get to experience it, I think you might have an understanding of why it was so impactful, these events. It has nothing to do with the science. It's just seeing it is just a visceral experience. So I would strongly encourage you, especially since this one's actually going to pass through part of Oklahoma, to take time off of your day. If you have family, take them with you, drag them if you have to. For me, this passes the mom test. My mom would have loved to have seen one of these, and she had no interest in science. And so I hope you'll see it. It's on April 8th in 2024, but you can Google it. Okay, that's my plead with you to do something about the solar eclipse. These are some questions. You can look through these. These will be posted in the file. There are quite a few questions here, and I kind of just grouped them according to their according to topic.